So the previous videos talked about how you test a combinational logic block. So if you have a combinational logic block, that's not very pretty. If you have a combinational logic block, now you know how to exhaustively test it, and you know how to test for individual node inside that combinational logic block. But that is, we've only covered how to do one of these simple blocks. But in an actual chip, if you have a digital design, you generally have some kind of memory. I wrote this as a flip-flop or a register going through the combinational logic and then back to a flip-flop or register. And there may be, 1,000 of these between like the pin on your chip. Pin on chip might give you the input to a register here. And then there might be like 100 of these flip-flop, combinational, flip-flop, combinational, flip-flop to an output pin. So let me actually do this. Dot, dot, dot. So you know how to test a single combinational block, but if it's embedded in the center of a chip where you have to go through 99 flip-flops or registers to get to that logic block, it's really, really hard to have control of the input of your combinational logic block. So a very common way to test, say, an individual, I'm changing my picture 1,000 times, but the way that, because it's also, there's a lot of cases where it's actually impossible to give the input to a combinational block by just controlling the pins here. Unless you maybe do a million cycles of your finite state machines or go through run an entire program or whatever it might be. It's almost, I won't say impossible. It's complicated to get the inputs that you want onto each combinational logic block that you want to test. So what is done for testing is, let's say I wanted to test this particular combinational logic block. However many inputs this has right here. I would insert a mux, and then I would have the value, the input value I wanted for that block on one of the inputs. I would put the value that I wanted to put on that combinational logic block. I'd put it on the input of a mux, and then I'd have a test signal, and this would have to come from a pin or if you have what's called a built-in self-test. Built-in self-test. And this is called a BIST, taking the first letter of each one of those words. This value for test and the value that you want to put into your combinational logic block to test it, those both have to come from somewhere. And we'll talk about BIST more, and we'll talk about scan chain and different things like that. But the basic structure around a combinational logic block is you get the value from someplace, you get this test signal from someplace, and it either does what your final circuit, what you want your final circuit to do, say 1, 0. Let's say test equals 0, then it's behaving like it did before you added the mux. If your test equals 1, now you're putting a controlled value into your combinational logic. Okay, so you also have to check the output of your combinational logic. So you have to figure out some way to get that value to the output. So what you do is you just do this, and this gives you the result of that. So now, if you have the value you want to put on the input of your combination logic block, whether you're testing for a single node or you're exhaustively testing it. Exhaustively testing it will mean that you probably have multiple values here that you have to put on the input and check each one of them, check the output. And then you need to have something to control that. And then you need to have something to analyze whether that output was correct or not. So this is the general structure of what's inside. The first way of using this, the mux and the testing the output, is called the ad hoc method. An ad hoc method means like there's one specific block, or 10, or if there's a million blocks and maybe there's 30 or 100, but you have specific blocks you want to test. You're not testing all blocks, and that is called ad hoc. Ad hoc, and you're just picking maybe one block or 1,000 blocks, whatever it might be, randomly, not randomly, but you're not testing everything. So ad hoc testing is you select target blocks and you only do them. And you only test them. And each one might have a little different kind of test. So that would be, let's look at how this might come about. If you have an ad hoc and you want to test just this combinational logic block, these values could come in from pins. So your input can come in from pins. That's a big cost again. If this had a 16-bit input to this combination logic block, let's say it was a multiplier or an adder or something like that, that could get expensive. It means you have to have a bigger package, and the packages are one of the bigger costs in fabrication right now. So it could cost you pins, and then the output, if you have the input and output going to pins, then you have 16 coming in. If it's multiplying, then you have 16 coming out. That's 32 pins you have to dedicate just to giving an input to this combination logic block and watching the output of the combination logic block. So that's expensive. So another way to do an ad hoc test is, if you know which block you want to test, what you can do is, all input and output to pins, that's option 1. 2 is, if you know what test you want to do on that combinational logic block, you can add something like a ROM block. And let's do that. I'm just going to take this picture right here to the dot dot. Add a ROM block right here. Add ROM, and now you need no pins for your input. Still have to figure out what to do with your output, and if you want to have this go out to the output, if you need more, if you're trying to debug as well as tell whether the test is good or bad, and we're not really worried about debugging right now. We're just worried about whether a chip is bad or not. If you want to maybe have more information to actually debug this block, then you probably want this all to go out to the pins. But if you just want to know if your chip is good or not, what you can do is add a comparator here. And hopefully in 133, you saw a comparator, a digital comparator, and you have, again, maybe a ROM here with the correct answer, and you say, hey, do these match? And this right here would go to an output pin. So all of this is inside. This test signal needs to come from someplace. That's probably going to an input pin. And then this would go to an output pin. And now, whereas before, if this was, again, at 16-bit in, 16-bit out block, then before, where you had to use 32 pins, now you're down to 2 pins. One to turn on the test, and one to see if that block actually worked. And this is considered this would be a built-in self-test. You have to tell the user whether it works or not. So you always need this output pin, and you don't want it testing all the time. So you generally need a test signal. But this would be considered a BIST, built-in self-test. It tests it completely and tells you whether it's right or wrong. And you can do any combination of this. You can have controls of the inputs, and somehow, I mean, this is harder, but figure out maybe you have a number of tests you want to do, or maybe there's only 2 outcomes from this block, or something like that, where you can give it an input from pins, maybe give it 16 inputs of pins, and have one pin output that just says whether it's right or wrong. Or you could have this all internal and maybe have all these, maybe all 16 bits of the output going to the output. You can do all sorts of combinations of this, and it depends on what you want to test, whether you want to be able to debug your block a little bit more, or whether you just want to know if that block works well or not. And generally, when there's a lot of pins out, that means you have to do some analysis on the receive side. So again, that adds some time. So that is your ad hoc version. And I'll go on to the scan chain in the next video.